So let me talk now about parsing. This is the thing that I don't cover in this class because I have never tried to cover it in this class, but whenever I've asked someone who has tried to cover it, they have sworn to me that it has not gone well. And part of this is it requires its own few weeks of time. So it can't be done in a rush. It requires time because it's confusing and it's detailed and involved. But you can't get through this class without knowing what a parser is. So I have posted a tutorial style notebook on how you would build a parser. And this notebook is available online. Okay? So let me start with what is a parser. So this diagram explains it all. So a parser takes your program, your Python program, or your, in this case, your Mython program, as a string or a text file, right? So as a set of characters in a file, and it constructs this internal representation, this AST, built using the grammar that we saw last week. So that's what a parser does. It goes from the user-friendly external rep to a internal rep that's a tree. And this is called an abstract syntax tree. Okay, so this is what a parser does. It's the very, very first stage of a compiler or an interpreter. So when you write a program, it's being parsed. So when you write a program in your Jupyter notebook, there is a Scala parser that's parsing what you write and building an abstract syntax tree, a Scala abstract syntax tree, that's then interpreted by the Scala interpreter. Okay, so the parser is an important piece, right? It's a very, very key and important piece of a implementation of a programming language. But it's also one of these pieces that gets requires a somewhat of an explanation. There is a theory behind parsing. It's called the theory of context-free grammars, something called LALR grammars. Okay, I learned it in my compilers class when I was an undergraduate. Those were the days when they thought compilers were super important, and so they used to teach us compilers. These days, compilers are still taught to be important, but they are considered more as a niche thing. There will be a few of you who are really interested in the subject, go to graduate school, get a master's, specialize in programming languages and compilers and know the ins and outs of JVM and system architecture and that's 2400 on steroids. And then you go ahead and write compilers for a living. Okay. The rest of you are just going to use these things. But when you use them, remember there is a parser that's doing things. So it's a technology that largely operates under the hood. Very few people end up, being developers of this technology. So it is taught very less often recently, but still it's a number one important research subject. Like lots of people like me care about it. So we build our own parsers for our own languages all the time. But, may not be useful for everyone. So we kind of don't teach this as much. Is everyone okay with the notion of a parser? Okay, so how do parsers get built? And I wanted to do a quick 20-minute overview of how parsers get built and maybe walk you through this nice library called the parser combinator library in Scala. Okay, if you are further interested in this topic, I am really happy to give you further readings, things that take you step by step and teach you this step by step. Okay, so let's start with parsers. All right, so let me go ahead. So let's do this. Okay, so there are certain kinds of languages that are easy to parse. So there's certain kind of syntax that's easy to parse. And this kind of syntax is called the Lisp syntax. Okay, so my goal here is to take arithmetic expressions, like suppose the user writes 2 plus 1 times 3 plus x minus y. I want to convert this into a AST representation. I want to convert this into something like plus const of 2, comma, plus const mult, so you get the idea, right? So you want to convert this into an internal AST. So this part is this part, and then you have minus ident of x, ident of y. So that's already a lot. So that's the limit of how much a user like me can write. Okay, and this is an example of converting something that's written in what's called the infix form to a internal abstract syntax tree. The grammar for this abstract syntax tree we already looked at last lecture. I'm not going to reproduce it, but you recognize something of like this was covered last lecture. Okay, and this is what parsing is all about. So parsing is all about taking programs in user-friendly notation that users have written, the way you have been taught to write programs, and convert it to something that's computer-friendly, that's computer interpretable. Okay. Now the interesting part here is there is a syntax that's very easy to parse called the Lisp syntax. Okay, and this is actually a very cool exercise we can all do. In Lisp syntax, you would write this expression in something called the reverse Polish notation. I don't know why it's called Polish, what about it comes from the country of Poland, but it's called the reverse Polish notation. And what's it? It's like this, it goes like this. So you write, instead of writing the argument first, you write the operator first. So you say plus, then you say 2, and then you say plus, then you say star 1 3, and then you say minus xy. Okay, and when you write it in like this is usually called Lisp notation, after a very famous programming language where everything is written like this, called Lisp. Okay, you might have heard of it, Lisp, and that's the programming language that came up with this notation. So if you write stuff in this notation, if you write your expressions in this notation, it's actually quite easy. There's an easy algorithm to take this expression and create this kind of an internal AST representation. Okay, it's a nice easy algorithm. I mean, you have to work it out. It's not like immediate, but if you work it out, you will come up with a nice recursive scheme for doing this. You scan the string one by one and you try and do this, and it's actually very it's a good exercise in designing these kinds of algorithms. Okay, but programmers typically don't like Lisp notations. I mean, there are Lisp programmers. By the way, there is a Lisp evolved into languages like that are used. There's a language called Clojure, and Clojure is actually a language that works on top of JVM. It's a Lisp that works on top of JVM, just like Scala works on top of JVM. So if you write programs in Clojure, then they turn out to be interoperable with Java programs and Scala programs. So a program in Clojure would really have this notation going all the way through. So you'd write your program like define a function foo with argument x, and then you would say plus x, something like this. So you write your entire program in this reverse Polish notation. Okay, so it becomes very easy to parse such programs. All right, convert such programs into AST is easy. But writing programs that in languages where the notation is infix is much harder. So when you write programs like this, int x equals 10, int y equals 20, for x equals 1 to 100, y equals y plus x, things like this, return y. So when you have programs including declarations and for loops and if statements and while statements, in the natural way you've been taught to write programs, parsing is harder. Parsing is harder. So what do? So the idea behind parsing is you write a grammar. But this grammar is different from the grammar that you've learned in class. This grammar is going to specify how does the user input get translated into the AST. Okay, So it's a different kind of grammar, okay? It kind of looks similar, but it's used for a different purpose. It's not used to define an inductive data structure. It is used to translate strings. So it's used to translate strings into an inductive data type. The string is my Python program, and the inductive data type is going to be the AST representation of that program. And we saw this yesterday. I showed you a program and I showed you how the AST of the program translates. Like we saw this on Tuesday's lecture. Okay, so let me give you a flavor of how we would write this kind of a grammar for something as simple as arithmetic. So I don't want to go to the entire programming language, though in my notebook, through stages, I show you how to build up the parser for the entire language, right? For the entire toy language. But I will show you for a small part of the toy language, which deals with arithmetic. Good so far? So one of the main issues with parsing has to do with something called ambiguity. It turns out the way we write things, even in arithmetic, you would think mathematics is the clearest and most precise of all human endeavors, right? Wrong, right? Even there, you would see, like even in grade school mathematics, there is ambiguity. There are things we don't bother saying out loud, but we do have a convention. Let me give you an example. What is this expression evaluate to? This expression should evaluate to 7, right? Does everyone agree that it's 7? Okay, but the reason you are doing that is because it has been drilled into you. You have been taught to read this expression one way and not the other. Imagine there are two ways of reading this expression. In one way of reading this expression, you read this expression as plus of 1 times or mult of 2 and 3. And this is the standard way of reading this expression. There is a slightly different way. You could have said, hey, why not read it like that, right? Why not read the plus? Why not scan the plus and read the plus before the star, right? So you could have said, well, I could have read it as mult of plus. I'm just going to write 1 and 2. You know there is a const around 1 and a const around 2. Okay, comma 3. You could have read it like this, in which case the value of this expression would have been 9. Okay. Now, what told you to read this expression as 1 plus 2 times 3 rather than 1 plus 2 times 3? Who told you? Do you remember? Who taught you to read it this way? I mean, we all agree, right? There's no disagreement here. But do you remember who taught you to read it this way? Let's see on chat. What do people think on chat? Yeah, the PEMDAS, right? Aunt Sally. Excellent. Right? So you had to be taught to read it this way. There's nothing natural about saying that, times comes before plus. It's a convention. We actually make this convention, and that's how it goes, right? That's how it goes. And the point here is there is a technical term for this, and this is called precedence. Okay, so it turns out that star has higher precedence than plus. So what this means is when I look at this kind of an expression, I take all the multiplications and I do them first. Once I'm done with all the multiplications, only then am I allowed to do additions. So you make a preference and you say, this is the preferred interpretation and this is not the preferred interpretation. So computers don't know about PEMDAS. They didn't go to grade school. They didn't have Aunt Sally telling them about that, as someone said on chat. So computers don't have Aunt Sally, right? So computers this has to be encoded in a computer. So when you're trying to parse this expression, when you write a C program, the C program has the PEMDAS rule built into it. So it knows that 1 plus 2 times 3 should be read as 1 plus brackets 2 times 3. You don't need to put the brackets. The computer knows to put the brackets for you and translate this to this AST. Okay? So that means that, how do we do that, right? So what we do is we write a grammar. So let me show you an example of how this grammar could look like. So this kind of grammar is not the same as the inductive definition grammar. So not the same as the grammar that we use for inductive definitions, but related. So it's called a context-free grammar. And what we do is we say, okay, this context-free grammar defines something called expression. And so an expression can be a term followed by the string plus followed by expression. An expression can be a term followed by the string minus followed by an expression. Or an expression can be a term all by itself. Okay? Now this kind of grammar is already different from the kind of grammar we looked at previously. It shares some commonalities. It's going to have non-terminals. Term and expression are called non-terminals. It's going to have terminals. The string plus, the string minus are called terminals. But other than that, it also has rules. So it says an expression expands to a term, the string plus, followed by expression. Okay? So it has rules, but the interpretation is completely different. The interpretation of these things is these things are generating strings. Okay? So what about a term? So you can say a term is going to be, let's call this, singleton, for the lack of a better name. All right, let me do this carefully. Let me call this single times term, or it's something as single divided by term, or it can be a single. So these are three rules. So this is the rule, this is a rule. I'm just not repeating it. Okay? And what's a singleton? A singleton can be just a variable, so it can be a string, or it can be a number, it can be an integer, or it can be an open braces. This is my version of open braces. So an open bracket followed by an entire expression inside followed by close bracket. So this is an example of a context-free grammar. And what happens here is when I input a string, so let me input this favorite string of ours, 1 plus 2 times 3. So 1 plus 2 times 3. A parser is going to come in and try to match different parts of the string with different non-terminals. Okay? So what does a parser do? And I'm not going into the algorithm for parsing, complicated stuff. Okay? It's not that complicated. It would take me about 3 to 4 weeks of, some fairly involved math to explain this to you. And it's, you get rather close to it if you take a class called Theory of Computation, 3434. They will explain a lot more. Still, they won't get into parsing because parsing is, again, slightly complicated. You build these things called parser tables and I had to do this as a student. Anyway, so if you take something like this, a parser will say, this one, I recognize this as a singleton because of this rule. Because of this rule, I recognize this one as a singleton. Well, I also recognize this as a term because of this rule. Because of this rule, a term gives a singleton. So this one, I recognize this as a term. This plus is just the string plus. And this 2, I recognize this as a singleton. This 3, I recognize this as a singleton. I recognize this as a term, I recognize this as a term, and then this is a star. So a term times term is, sorry, here you go, you have this rule here. So you would say, a term times term is a term, okay? And then a term is just an expression. A term plus expression is an expression. So what a parser does when it sees a string like this is it starts to recognize parts of the string as matching particular rules and therefore particular non-terminals, and it builds bottom up, okay, this derivation rules until it gets to recognizing this whole thing as an expression. All right, and then what the parser does is using the sequence of rules, the parser builds the AST. The parser builds the AST using a slightly interesting thing called syntax directed translation. Okay, it builds the AST and it converts this string into this kind of a term, this kind of an AST. It's a complicated algorithm. We take it for granted, and I'm not going to teach it in this class. But note that it exists. It's there, and it's not something that I want you to learn in this class, but I want you to know that it exists. Every time you write code and you run an interpreter or you compile it, you run GCC, this is happening. This is the first step that's happening.